you. Okay, so let's make a start. So a lot of what you've been doing over the last, I don't know, 2-3 days, just before the weekend, is that we've been developing theory, and most of the exercises you've been doing are involving choosing a Hamiltonian containing as much of the physics of the problem as you can, complex optical potentials, two-body interactions to bind things, real interactions to scatter things at low energies in CDCC and whatever, okay? And the approach so far has been to take this Hamiltonian to solve the Schrödinger equation essentially exactly, okay? Couple channels, methods, whatever, but you've got a Hamiltonian and you're trying to find an exact solution of that model problem, okay? So today and tomorrow we're going to take a slightly different point of view, that sometimes an approximate solution might be good enough, and sometimes an approximate solution, approximate approach may make it easier to calculate some things which are very difficult to calculate if you try and solve them exactly. Okay, so I'm talking about the first of these general methods today, applicable at high energies. I'll call it the Eikonal methods. Okay, many people call these sort of methods diffraction theory or Glauber theory, but I try and avoid the word Glauber theory because Glauber is used for many, many things. There's many different, slightly different ways of treating things, and so Glauber theory means different things to different people. Okay, so what I want to do is talk about solutions of the Schrödinger equation when we make a specific physical assumption, namely we make the Eikonal approximation, and to cut a long story short, the basic idea of this is that you're sufficiently high energy that most of the scattering goes in the forward direction. Okay, you've got reactions which are very forward focused, and if they're very forward focused, you can say the angles of scattering are very small. You can make some approximations to obtain some expressions which have a rather simple structure, and that's what I want to try and bring out this morning. Okay, so before coffee, I'm going to talk about really take the Schrödinger equation for two particles scattering from each other. How do you solve that Schrödinger equation in this approximation? And that will allow you to calculate elastic scattering and such things of point particles scattering from each other. Then I'll go on to say how we generalize that for composite objects. Okay, the sort of halo things you've been thinking about, boron 8 or beryllium 11 in the last couple of days, where the nuclei look very much like a big bit and a little bit hanging on for its dear life with very, very weak binding. Okay, and then we'll generalize this afternoon to a different sort of situation. Okay, so this is what I want to talk about this morning. I think I've said most of this already. I want to discuss approximate solutions of the Schrödinger equation for states of 2, 3 or more bodies. Okay, Antonio showed with the couple channels method, and he hinted how difficult it was to solve for a 3-body projectile scattering from a target. And we heard the words Faddeev equations and things like this, okay? And using things a little more approximately, such as using this Eikonal method, I've certainly done calculations before for a 5-body projectile. And I say the approximate structure allows you to do more complicated systems, not with full accuracy, but at an accuracy hopefully where you can get useful physics. Okay, so we can do this by introducing this Eikonal or forward scattering dominated approximation for the reaction dynamics. Okay, so I want to reiterate this thing that we've been talking about called the S matrix, what it means physically, because we'll have equations which, if you understand what the S matrix is doing, they're much easier to read and to interpret. But we've met the S matrix many times now, so we'll talk about its Eikonal version of that. And we're moving into the semi-classical realm, so instead of having discrete angular momenta 0, 1, 2, 3, 4, we'll have a continuous variable which represents the impact parameter of the two scattering objects, and that's going to be those ideas will be extended tomorrow by Antonio. And because it's approximate, part of what we're doing this morning was to at least gain an idea of what sort of accuracy we might expect from these sort of methods as a function of energy. Okay? If your scattering energy is too low, this is unlikely to be good for several reasons, including the fact that the scattering is not very forward focused in the way that I'm discussing. Okay, so one of the other things we're trying to do is gain an impression of how accurate this method is, and so when you should be able to use it and when you definitely should not think about using this approximate solution. Okay, so we're talking about, from an experimental point of view, so we're talking about radioactive ion beam physics here, if that's the physics we're interested in, at fragmentation facilities. Okay, so I don't want to really go below about 100 MeV per nucleon. Okay, and you'll see why when we look at some of the pictures later on. So the sort of physics that we're addressing is what goes on or will go on at FAIR and has been going on at GSI. The new radioactive ion beams facility, RIBF, in RIKEN works at about 300 MeV per nucleon, which is an ideal energy for these sort of techniques. The NSCL, around 100 MeV per nucleon, and FRIB proposed will work in the similar sort of energy region as RIBF of around 300 MeV per nucleon. Okay, so there's a range of facilities in the world where beams are produced with these sort of energies, and for these sort of energies, these sort of techniques can be very valuable. Okay, there are other facilities in the world, such as Isolde, what will happen at Spiral 2, Triumph, where these techniques are definitely not applicable. Okay, but knowing about these techniques, you can learn some physics also. Okay, so let me just remind you. So the way such facilities work and the way we end up with these exotic beams, which is what I'm going to be discussing, is really brute force and ignorance. So let me just remind you, the way exotic beams at high energy are performed is you smash something on something else. You get disintegration with the random removal of neutron and protons, and so we get some object here with an interesting collection of neutrons and protons, with not necessarily in the normal ratios for stable nuclei. They cool down and they're traveling forward still very fast, and that's the thing that we do experiments with. Okay, so it's a lot of hard work to produce these things and separate them, but say it's these guys that are produced in fragmentation facilities with energies of typically 100 MeV and greater, which are the discussion. And I'm interested in these techniques because I say, if this happens to be silicon-42 or sulfur-44 or something really exotic, it would be nice to have some general techniques for working out what are the structures of the nucleons, what's the single particle structure of these objects which are produced and which cost a lot of money to produce. So we want to do some spectroscopy on those, and we'll see how we can do that later on this morning. Okay? In an approximate fashion. Okay? Let me not stress, I'm not looking for exact solutions here. We're using the particular aspects of the energy and the dynamics to try and obtain approximate solutions that tell us specific useful information about these systems. Okay, so let me return to this one. So when I showed this diagram last, I had 10 MeV per nucleon and 100. Okay, so now we're much more interested in starting around 100, going up through 250, which is where these facilities work, and GSI works somewhere sitting over here at a larger fraction of the speed of light. Okay, so I want to remind you of these time scales in terms of our typical direct reaction clock, which ticks at 10 to the minus 22 of a second. Okay, so at NSCL energies and 100 MeV per nucleon, we've got 100 MeV per nucleon, so the gamma is about 1.1. That means it's 42% of the speed of light, or thereabouts. And we've been talking about these collisions which graze the surfaces. The interaction will operate over some distance d of a few Fermis, maybe a small number of Fermis, just a few. And so we're talking about time scales for this interaction here of the order of 8 times d times 10 to the minus 24 of a second. Okay, and if you've got 300 MeV or 250 MeV per nucleon, you don't gain so much. Okay, it's going faster, but there's square roots and things operating, so you don't gain so much. Okay, but we're down in the 10 to the minus 24 of a second times a few. And that means these are very fast collisions. There is no great time for nucleons to rearrange themselves, to move around in the nucleus during that time. literally they come together, bang, and they're past it. And then if something has happened, it's happened. And if nothing has happened, it's not going to happen any longer. Okay, so I say very often the analogy I use, it's not a good idea if it's not a good idea to stick your head out of a fast-moving train trying to read the numbers on one of these posts at the side of the railway line. Okay, things happen fast, and that's what we're talking about here. Okay, very fast interaction times. Okay, so that sets the time scale. That sets the scene a little bit. Okay, so this is what we've been doing. I've thrown away the spin labels, etc. This is basically what we've been doing over the last days. Is that we've been solving the Schrödinger equation using differential approach, and so in this simple model where you've got two bodies interacting via some potential energy, we get the exact answer by solving the three-dimensional differential equation. And traditionally I've called this thing a distorted wave, but say if all there is a complex interaction U, such as I've written down there, with a Coulomb piece, a real piece and an imaginary piece, if you can solve this exactly, then you have the exact solution of the problem. Okay? And the way we've been doing that is to divide this thing into a partial wave expansion. And as I say, I'm avoiding all the complexities. This is the important bit of a partial wave expansion. You look at the scattering in each orbital angular momentum between these objects, and we end up with a set of radial equations to solve for these relative motion wave functions. Okay? Okay, so we've done that many, many times, and we've done it on the computers here, and we've done it in Fresco, and we've done it with a variety of tools, and we have solved this equation. Okay? And what I need for today is to remind you that these solutions at large distances and will look like incoming waves. We should be very familiar with this expression now. There's these negative going H's, which tell us there are incoming waves in this partial wave with unit amplitude, and the outgoing waves have an amplitude S, which is the partial wave S matrix amplitude, multiplying outgoing waves. Okay? And I think we've all said it. I've said it. Philomena said it. Antonio has said it. That this S, once you know those numbers, those complex numbers, you can calculate any observable in this problem. Those are the amplitudes of the outgoing waves and tell you the amount of stuff, the amount of particles that reach your detector at large distances. Okay, so this is the diagram again. And say I want to stress this because we're going to see things like this and things like this later in the day. Okay, not much later in the day, but later in the day we will see things like this and see things like this. I want you to remember what those things represent. Okay, so S is the coefficient of the outgoing waves, okay, and the modulus squared of S then tells me the probability associated with the particle surviving the collision and coming out after the reaction has taken place. Okay, so I often think of this as a survival probability. Particles come in angular momentum L, and some of the time there will be an absorption event and they'll excite the target, those P's and Q operators that we talked about along the way. Okay, but this quantity tells me when I see something like that, I hope you will register that this particle has survived this collision, has come out and can be detected. Okay, whereas that quantity, therefore, 1 minus that probability must be, this is telling me that this particle didn't make it. Sorry. Okay, it came in, there was an inelastic event represented by the effects of the imaginary part of the potential, and the particle got absorbed in that imaginary potential, which means that it inelastically excited the target during this collision and did not emerge as an elastically scattered particle afterwards. Okay, so I hope when we see this we can say survival, outcoming particle, that tells me a reaction took place, and this is the probability that the particle underwent some more complicated reaction and did not emerge from the collision in the elastic channel. Okay, so that is going to be important later. Okay, so we've done this many times, but it's going to be really important later when those things pop up to remember what those are. Okay, so let me just say a couple more words about this semi-classical approach. I showed a slide something like this on day one. okay, as an introduction. But the idea here is I'm now talking about relatively high energy collisions. Some of the particles colliding will also be heavy, so heavy ions scattering from heavy ions, so the momenta will be large, which means that the K values will be big. Okay. If the incident particle is a nucleon, then the K value won't be so big, but so it'll be harder with a light particle to get up to the big Ks, which I would really like for these approximations to be working well. Okay. But the idea is, if you're at high energy that we've seen, this is the nature of this S matrix element. It's modulus. Okay. And again, I think we've all said this. For some partial waves, up to a value such that we hit the radius where the two surfaces of the nuclei just graze each other, there will be absorptive events due to the imaginary part of the potential, and the modulus of the S matrix ent is typically small. As we go to larger L's and we get to the surfaces where these things just graze each other and then cease to hit each other, this S matrix element climbs to 1, indicating that these two particles simply transmit past each other. Okay. So in this S matrix element, there's an absorption phase at low angular momenta and a transmission phase at larger angular momenta. And once again, this is supposed to show that as I go to higher energy, many orbital angular momentum contribute to the reaction. Okay, there aren't just 3 red dots, 0, 1 and 2 values of L. There are many values of L that contribute, and it's a reasonable description looking at this to say I can represent that S matrix via a smooth curve just as well as I can represent it by these individual dots. Okay, so rather than doing sums over discrete angular momenta, we will be doing integrals over an impact parameter. Okay, and being a little more precise than we were last time, the relationship between okay, so let me just say, so we've been talking about an S of L when you do coupled channels calculations. I'm going to start talking about an S of B, where B is the impact parameter, and as I say, being a little more careful, the relationship between the fully quantum discrete angular momentum index L and the continuous impact parameter index B has this 1/2 kicking around in there. It's neither here nor there really, because if we're talking about high energy collisions, L can be a very large number, and so that little extra 1/2 there doesn't really matter very much. Okay, but you will see that when we've been writing expressions for cross sections, and we've had things like the sum from L is equal to 0 of some stuff weighted by 2L plus 1 to correctly count the substates associated with each value of L, you'll see that with this translation here, those sorts of sums over the discrete index will turn into, just using this relation here, this will turn into 2k squared times an integral over B. Okay, so instead of having these guys, we're going to have these guys here. Okay, and you can also see that the centrifugal barrier L into L plus 1 over R squared is essentially K squared B squared over R squared. Okay, so we're moving away from L and we're moving over to B, and they do basically the same stuff, but the equations look slightly different. Okay, so as we've already discussed, any sort of cross section you want to write down for such systems is written as some sum over partial waves. Okay, so the reaction cross-section for the system I've just been talking about would be pi over k squared times this combination of symbols on the right-hand side. Okay, and you can see that pi over k squared times the sum 2L plus 1 is exactly what you need to turn. These factors there are just telling us that actually I'm doing an integral over all impact parameters of an S matrix elements now with a continuous variable. Okay, so we will get used today to cross sections that look like combinations of stuff like this, okay, rather than looking, and they're much simpler, aren't they prettier than all this pi over k squared sum 2L plus 1? What's all that rubbish? Okay, what we've got here, we've got a collision at some impact parameter, and I have to integrate over all possible impact parameters at which that collision can take place. Okay, so we've got this thing here, 1 minus s squared. Remember that? That's the probability that the thing does not emerge from the collision. So that's telling us a reaction has taken place. And so this is just a reminder that the total reaction cross-section is just this factor, the probability that something has happened at impact parameter B integrated over all impact parameter will give you the total reaction cross-section for this two-body system. Okay, so you can go back and look at this, but to say what I mean by this integral over all impact parameter is that, well, there's impact parameter. It can be anywhere around this circle. So there's an integral over phi, and the area of each little annulus as you go out in B is, of course, b dB times 2 pi. 2 pi b dB is how much area there is in each little shell as you look around the impact parameter plane. Okay, so as always, just shout if it looks as if there's 2 pi's or anything else missing, or you think I'm talking rubbish. Please shout. Okay, so let's talk about doing this alternative way. In the semi-classical continuous variable, what does the iconal approximation mean? Okay, so what I'm going to do in the next slides is show how we can obtain an approximate solution of the Schrödinger equation by making one approximation, essentially. Okay, so here we are. There's our Schrödinger equation again. Okay, so that's the guy we would normally want to solve, and then this is trivially just multiplying through by the 2 mu upon h bar squared factor. Okay, so this is the exact solution. And the iconal approximation starts by saying, let's assume that this wave function here, this exact solution of this Schrödinger equation, looks like the instant plane wave, which has to be there, that's the instant boundary condition, times a function omega. Okay? So what this says that this distorted wave is going to be modified from the plane wave, because there's a potential in the Schrödinger equation, and so this omega in some magical way is taken into account of all the effects, all the departures from the plane wave due to the scattering event. Okay, so all the effects of u sit in this function omega. Okay, now I haven't made any approximation here. Okay, I'm just saying this function I'm going to represent as a product of 2 bits, and now if I substitute this assumed form for the equation into the Schrödinger equation, I can find the equation which omega must satisfy in order that this is indeed a solution of this equation. Okay. So that's what the next line does. I substitute this into here. I differentiate the products because they're products now, and if I do that, I get this guy sitting down here. Okay. So if this is to be an exact solution of this Schrödinger equation, omega must satisfy this differential equation here. Okay? So you may think I'm onto a loser here. Okay? I started with something which we know and love and looks so terribly simple, and I've got this hideous looking differential equation now, which not only has a del squared term, but it has a grad term in there as well. Okay? But we can make this rapidly simpler by selectively throwing a term away. Okay? Now, what's your guess? Which term in here would be top of your list to throw away in terms of the physics that you think is going on? What's k supposed to be? What is k? K is supposed to be big, isn't it? Yeah. U is the potential. If I throw u away, this isn't going to be terribly interesting. Okay, that's the scattering. So looking at this, if I wanted to get rid of something to make this simpler, my eyes would focus on this guy here. Okay, so just thinking about your normal mathematics, what does a gradient tell me? What does a derivative tell me? Derivative is 0. Derivative non-zero. So derivative tells me about slope. All I want, simple things. Tells me about slope, rate of change. Okay. What does a second derivative normally tell me something about? Shout. Curvature. Curvature. Okay. So, right. So this can be big if things change, have a slope. This is some sort of curvature term. Okay, so if I throw away this term, somehow I'm going to throw something to do with curvature away. Okay, and maybe it's the curvature and the trajectory. Okay, so maybe if I throw that term away, I'm assuming that the trajectory is a linear one. Okay, well that's what turns out to be the case. Okay, but say you can look at this and say, if you were a betting man or betting woman, and you looked at this and you wanted to simplify, you certainly wouldn't want to throw that away, because there's K there, and we're supposed to be at high energy, and K is supposed to be big. So that term is whatever. Okay, so let's think about throwing this term away. Okay, the other thing on this thing that we'll get back to in a moment is when might it be good to throw that term away? And the usual argument is that these sort of methods that I'm talking about here will be good when the potential energy over the energy is small, and K times A being some sort of diffuseness or rate of change of the interaction, that product is greater than 1. Oops, beg your pardon. Okay, so you can see that the way you get to this point is to make K big and not have too sharp edges on your potentials. Okay, and we saw right from the start of the course that diffuseness parameters for a nucleon, or the surface of a nucleus, are what, 0.7, 0.6 Fermi, something of that order. So K doesn't have to be that big before this number starts to get bigger than 1. This may look a bit ominous, because you know potentials of nuclei with nucleus can be reasonably big, but remember, we're not talking about reactions here. My picture and the direct reactions means that these things happen at the surface. Okay? We've got grazing collisions. We're not talking about things that get deep into the nucleus. If things get deep into the nucleus, there's inelastic events and absorption, and those don't contribute to anything really. Okay? They're in the 1 minus mod s squared. So what we're really talking about is at the surface, where the potentials, you're in the tail of the potentials, or the potentials are lesser, is the energy high enough so that in the important region of space where we're interested in, this number is less than 1. And that can be readily satisfied in such systems if the energy gets large and if the reaction is peripheral. Okay, so let's proceed then, because we won't get anywhere. Okay, so here we are. So neutral particles. I'll put the Coulomb force back in a moment. Let's for the moment forget about Coulomb forces, and we'll put them back afterwards. Okay, so this is what our intuition might suggest. Let's think about what happens if I can take that term away. And there's a little exercise on a little do on paper exercise this afternoon. So I'm not going to dwell too much time on this, because I think you should go through this yourself, okay? But so I'll go through it quickly. But let's throw that term away, that term which is something to do with curvature in some very general sense. Let's throw that away, because I think we may have an inequality looking like that. There's a factor of 2, there's K, which is big, this is the slope, and slopes invariably are bigger than the curvatures. So let's assume we can throw that term away for various reasons. Okay? So we got slow spatial variation compared to the value of K. Okay? And so that means that I've got 2K dot grad and whatever. Okay? And you can see if the K vector there is in the z direction, as we normally define it, the K points in the z direction, so the only component of the gradient I need is the z component of the gradient. Okay, dot product. So if that's K dot z hat, or whatever your notation is for vectors, I only need the gradient component in the z direction. So this equation here, which looks rather complicated, well, this guy is not 0 everywhere, okay, the plane wave, so it's what's in the square brackets that has to be 0 to satisfy this differential equation. Okay, so having thrown that away, recognizing that K points along the z direction, that what was a horrendous looking equation for this thing earlier on now looks like a very simple first order differential equation. D by dz of this modulating function is minus a constant times the potential times omega. Okay, and I claim, you should do it later yourselves, that the solution to this equation is very simple. It's this. It's an exponential of an integral. An integral along the z direction through the potential energy that we've got there. Okay? So many of you probably can sit there and you can differentiate this and convince yourself that it satisfies that differential equation immediately. Okay? But if you can't see it immediately, you can spend some time doing it. You'll have to believe me for the time being. Okay, so what we've got here is an integral. It's a one-dimensional integral, so we don't have to solve a second-order differential equation or anything. To get omega, all I need to do is a one-dimensional integral over a straight line path in the z direction through the potential at impact parameter B. Okay, so let me go to this one and then I'll come back. Okay, so this is our picture. I've got a particle, some impact parameter B. Here's the potential. It has some finite range, and after some radius we can contend it will be negligible. And what we've got here, doing this integral, then I select some impact parameter and I have to integrate along this path from minus infinity to z. That's what it's said to do. Okay, integral from minus infinity. So down there we come into the interaction zone, and if I want omega at the point z, then I stop doing that integral at that point z. But you can see that as I travel along the z direction, omega gains this exponential behavior, and part of this will be a phase, part of this will be part of this will change the magnitude of omega, part of this will introduce a phase in omega, and this phase will grow with z as I pass increasingly through the interaction region. Okay, so this is what we've got here. Okay, so that's what omega is. So that means that our scattering wave function, our approximate solution of this three-dimensional Schrödinger equation, looks like our plane wave times omega, and now we know what omega is. It's what's in this box. So our solution looks like this. Okay. Now after the collision, of course, the particle comes in from z is equal to minus infinity. It trundles along, it goes through the interaction region, and it comes out the other side. So what we're really interested in is what happens, the collision having taken place and the particles coming out the other side. What we're actually interested in is what happens as z goes to plus infinity, because the particle is then heading towards our detectors. It's passed through this range. Okay, so you should be able to see that after the interaction, as z goes to infinity, the only thing that happens is that z up there tends towards infinity, and then the solution at large distances in the positive z direction looks like a plane wave times this guy. Okay, this guy no longer depends on z. Z has been integrated over in here, so this is a function only of the impact parameter. Okay, and moreover, this quantity here multiplies the forward-going waves after the scattering. Okay, so this object here is our iconal variant of what we would call the S matrix. Okay, because after the collision we have forward-going waves, and the probability amplitude of those forward-traveling waves, the probability that they're going to get to the detector, is what we have interpreted to be the S matrix element. Okay, so in this, doing things this way, this partial wave S matrix, instead of solving a differential equation, matching to asymptotic boundary conditions of outgoing waves, etc., to calculate the S matrix element as a function of B in this way of doing things, what you need to do is a one-dimensional integral at each impact parameter through the potential energy that is relevant. Okay. Now, if this is all it did for us, then it really doesn't help us very much. Okay? If this is all it did, there'd be no point, because it's easy enough to solve the differential equations exactly, and you've been doing it for the last days, and codes are available to do that, and if you get the parameters right, Fresco will do that for you. But the philosophy of doing this is not because it saves us time and allows us to avoid solving differential equations. The real advantage of doing this is that when we don't have just a simple projectile here like a nucleon or an ion, when we've got some composite objects, maybe helium-8 or helium-6 that we talked about yesterday, when this is a composite object, this theory generalizes in a very simple way to few-body projectiles. Okay, that's where the power of this method is, not really in the fact that the S matrix is easier to calculate. Okay, so one thing we can do later on today, if we like, is we can compute this You can take an optical potential, you can compute this for various values of B, and you can plot it, and you can see what exact solution of the Schrödinger equation gives you for the S matrix. And you can compare those two, and by doing that at different energies, you can gain an impression about how good this approximation is as a function of energy. Okay, so this is the summary slide, okay? So this is the iconal approximation. This is really what happens, okay? This is our solution for the three-dimensional scattering solution as a function of vector r. This is the physics that's being represented. We've thrown away curvature, and we've ended up with a problem which involves simply integrating along a straight line path, okay? That doesn't mean we can't calculate the differential equation for a particle scattering through 10 degrees or 15 degrees, okay? All it's happening, it says, I can get a reasonable approximation to the S matrix by calculating the effect of the interaction along a straight line path. So what we're saying here is that in the vicinity of the collision, it is a good approximation to assume that these two particles pass each other moving in the forward direction, and the whole effect of the potential is given by the integral of the potential along the path travelled by the particle in that interaction. Okay, and this is our S matrix. Okay, so I hope these things will start to become familiar as we go through the day. But to say there's really only one approximation we've made. Okay, we've thrown away a term saying del squared omega in that derivation. That is what we've done. Okay, so this is the advert for what's to come. Okay, so I say the power of this method is, don't think too much about this slide. The power of this method is if instead of having just an elementary particle coming in, say I had 2 alpha particles and 2 neutrons, what would that be? Beryllium 10? You know, if I wanted to describe my projectile as 4 particles coming in, 2 alphas and 2 nucleons, then these components of the projectile are going to pass through an interaction region, okay? And the iconal approximation, we'll go through this later, for a collection of particles such as that. What turns up is that the S matrix element for the collection of objects is just the product of the S matrix elements for the individual bits. Okay? In other words, if I've got nucleons and alphas, if I calculate the S matrix by integrating the alpha potential through and the S matrix by calculating a nucleon potential through, then what I should do if I've got a collection of stuff is the relevant S matrix is going to be an S for alpha 1, an S for alpha 2, an S for nucleon 1, an S for and just the multiplication of those 4 with each other. Okay, so you go from individual particle scattering to collective particle scattering with a very simple procedure in this. Okay, so we'll do this derivation in a little bit, well, not very much longer, but in a bit, and we can see how that works. Okay, so how would we go from this S matrix that we've just been discussing to a differential cross-section for elastic scattering, for instance? Okay, well, the way we would do that is to go backwards, take a step back and say what is the definition of the scattering amplitude, and this is an exact formulation in the integral form. Okay, remember what you've been doing with Philomena and others. There's a differential form for doing things and there's an integral form for doing things. Okay, and an exact expression for the scattering amplitude for the scattering of a point particle looks like this with some constants, some phase space constants. Then we have a plane wave here which contains the direction of the outgoing particle after the scatter. This is the interaction, and this is the exact solution of the Schrödinger equation. Okay, and as other people have said, this is a formal expression. Normally it's not terribly useful because I want the scattering amplitude to tell me the answer, but the answer requires the exact solution, so I've solved the problem by the time I get to this point in any case, but because I would have to solve that. Okay, but this is our starting point. Now, what we've got is not an exact wave function, but we've got our approximation to the wave function. Our approximation to the wave function looks like a plane wave times our modulating function. Agreed? Okay. And so we plug that in there because that's our best guess for this. And if I plug that in there, I can compute the scattering amplitude for elastic scattering based on our approximate wave function here. Okay. You'll see that if omega was 1, then this is just Born approximation. Okay. Plane wave here, potential plane wave on the other side. And so what this is doing is make an improvement to Born approximation, because our omega is certainly not equal to 1. It's this exponential form that we've been discussing. Okay. So I can take the plane wave over the side as we normally would, interpret this as a momentum transfer Q, and omega sits on the other side. Okay, so working out the elastic scattering amplitude for scattering at an angle theta involves us working out something like this. Okay, and as you're also familiar, almost certainly from undergraduate work, if omega was 1, this would be just the Fourier transform of the potential, and that's the result you get from Born approximation. Okay, so now we can make some other observations. Okay, remember we're talking about large K is the regime we want to be in. Large K and small scattering angle. Okay, so if I look at the situation here, here's K incident, here's K scattering at some small angle, and Q that comes in here is K minus K prime. And if you draw the vector diagram, you'll see that K minus K prime, if the angle is small, Q here is essentially at right angles to K. Okay, so this is just vector. All right. So if you forward scatter, the momentum transfers essentially at right angles to the direction of travel of the incident beam. And okay, so Q, in other words, Q does not really have a Z component, and so Q dot R in here is essentially Q dot B. Okay. B is the impact parameter, which is the component of R at right angles to the beam direction. Okay. So that's the second approximation we're going to make in looking at the differential cross-section for elastic scattering. We'll assume the model that we're primarily interested in the scattering to forward angles. Q is essentially at right angles to the incident beam direction, and so the only component of R that we pick up is the impact parameter B. Okay, so let's go back one step. So this is our expression we had on the previous page. Let me remind you that when we did our derivation, the equation that omega satisfied was this one. Okay, you won't remember it, but it was on the previous slide. The first order differential equation that omega satisfied, which gave us that exponential solution, was this one. Okay, and you'll see that this combination of u and omega is exactly the same thing that appears in this expression for the scattering amplitude. And so I can replace this pair by a constant times the differential of omega with respect to z. So this integral here, putting in the fact that Q dot R for forward scattering is Q dot B, and putting in the fact that u times omega is the derivative term here, then I can write down the iconal approximation to this scattering amplitude by this set of terms here. Okay, and there's a z integral that can be done. There's this is a two-dimensional plane wave now. Okay, I've got an integral over impact parameters. This is a plane wave Q dot B, and I say if you haven't met this stuff before, then it's a matter of sitting down with your favorite handbook of mathematical functions. But when you do the integral over the azimuthal angle phi of B, and look at what this is, then this amplitude involves a Bessel function, not a spherical Bessel function, but a Bessel function of big J in the cylindrical coordinates and the S matrix element that we have calculated before. Okay, reminder of what S is here. Okay, so the normal way of doing it, what you do when you want to work out elastic scattering amplitude is you solve a lot of second order differential equations, you compute a lot of partial wave S matrix elements, then you do a sum from L is equal to 0 to infinity, and you sum up some stuff with Legendre polynomials and all some other stuff in it. Okay? What you do when you do it this way is that you have to choose your potential, then you have to construct your S matrix by doing the integral through the potential at various impact parameters. So you do a lot of one-dimensional integrals to find this guy. Then once you've got that guy, You put it in here and you do one more one-dimensional integral, integrating over all values of the impact parameter, and work out this linear combination here. Okay? So in many ways it's a numerically more simple procedure. As I say, numerically simple does not mean that's the way you should do it. As I say, the advantage of this technique are really much stronger in terms of other things it allows you to do. Okay, so let's okay, so there's a little code which, if you want to run this thing, you can work out the scattering amplitude, work out the differential cross-section, doing it this way, and you can compare that with what Fresco or your favorite elastic scattering program will do, and compare the two and see how they do. Okay, I'll show you an example in a moment. Okay, so I'm not going to spend much time on Coulomb. Let me just point out what the difficulty is. Coulomb is always problem. Okay, Coulomb goes on forever in space. It just goes to very large distances. Okay, and that is the problem with the Coulomb force. And the problem with the Coulomb, if you try and do it this way, is that this is our function that involves the integral of the potential along the z direction, right? And the problem is if you try and work out this phase that comes about by integrating the Coulomb force along the z direction, then that direction does not, that integral does not converge. It gives you a logarithmic divergence. Okay, so if you just try and apply the iconal model here by integrating along z through the potential, and the potential happens to be a 1 over r potential at long distances, you know that integrating 1 over x's, 1 over r's gives you a logarithm. Okay, and so this diverges. Okay, so you have to do a technical little trick. There's always a technical trick when you're dealing with the Coulomb force. Okay, and the way you would do it here is you say, well, I know the Coulomb force is long range, but in physical reality, these nuclei have electrons around them, and when I get sufficiently far away, there is a screening radius, and beyond some radius, which is very large, these particles in reality never see this nucleus any longer. They're beyond electrons or doing some other stuff. Okay, so you can formally solve this problem by screening the Coulomb radius, the Coulomb potential large radius. So instead of integrating from minus infinity to infinity, you integrate from minus a to plus a in your head. Okay, you do the integral with an upper limit, and then you see what the effect is. Okay, and the effect is as follows. Just as in the partial wave way of doing things, the iconal amplitude becomes the sum of a point Coulomb charge. You can pull the point Coulomb amplitude out the front, and then you get the extra scattering due to nuclear in the presence of Coulomb. Very similar structure you've had before. Okay, and this guy, this large radius that you cut off at, you can show if you do the analysis, and I'm not going to do it for you, is that this appears as a phase sitting out the front. Okay? The only place that screening appears is that there becomes an overall phase that sits at the front that depends on that screening radius. But when you take the modulus squared of this to work out a cross-section, any overall phase does not matter, and it does not enter the calculation whatsoever. Okay, so this is in the slides if you want to study it in detail, but say there's a little trick. The structure of this amplitude is very, very similar to what you get when you do partial waves. Point Rutherford scattering plus the additional complications due to this is very similar to the iconal, the amplitude I just showed you, except there's a phase in here. Remember the e to the I sigmas that come about in your partial wave expansion, and this S matrix is slightly modified because this contains, in addition to the nuclear interaction, this S matrix will contain the fact that the Coulomb interaction you use at short distances is not 1 over r. So there's an additional departure from the 1 over r at short distances due to the uniform charge distribution you normally use, and that bit must be included in the interaction that you calculate as being a departure from the Coulomb, the point interaction. Okay, so here's some calculations which were done some time ago, and they're in an energy region where you might or might not think we're high enough to do for this approximation to work. Okay, so this was deliberately done this way. So here's some S matrix elements, and the black curves are exact, so they're solving the Schrödinger equation partial wave by partial wave. And this is 10 MeV, 25 MeV, 50 MeV. Okay, all of those are really too low to expect that the nucleus interaction will be well described by this iconal picture. Okay, so all I'm showing you is that as you go up in energy, things get better, but by the time you've got to 50 MeV per particle, you're not really there yet. Okay, so this is the S matrix. So the dashed curve you should compare with the solid curve. Okay, at 10 MeV, the iconal matrix does not look much like the real one, and as you go up in energy, they're starting to converge on each other. And I'm suggesting that you might like to look at this at 50 and then look at 100 later on and compare and see how you're doing. This is the cross sections over here. Okay, so this is the cross section for neutron carbon-12 scattering at 10 MeV, 25 MeV and 50 MeV. And once again, you should be comparing the dotted curve and the solid line. And things are getting better, but still at 50 MeV, we're not, even at the smallest angles, we're not doing great. Okay, so obviously you need to go higher than this in the nucleon target system to get sensible accuracy from this technique. Okay, now when you have a heavy particle, such as this is the same thing for beryllium-10, scattering from carbon-12, at 10 MeV per nucleon, 25 MeV per nucleon, and 50 MeV per nucleon. And this is the ratio to Rutherford elastic scattering on this side. Okay, and you can see as you go, because this is a heavy ion with a much larger K, it does much better. Even at lower energies, it's already doing better than the light particle did. And you can see that the cross-section out to 15, 20 degrees is doing reasonably well by the time you get to 50 MeV per nucleon. And as you go down, as you go up in energy, things get very better. Okay, so and you can see that it's starting to give a reasonable description of the S matrix. Not perfect yet, but it's getting better by the time you get to 50 MeV. So you may, again, I'm suggesting you may want to do 50 and 100 MeV per nucleon and see how these things are developed compared with the exact answer. Okay, so this is what we do. Okay, when we have an approximate theory, we have to make contact with the exact methods and try and assess the precision of the method whenever we can. Okay, now, so let me now move on to composites. Okay, because I said that's where this method really comes into its own and has some really positive ways of doing things which are very difficult to do using partial wave and coupled channels methods, for instance. Okay, so I want to now think about, for the rest of this morning before coffee, I want to think about elastic scattering of composites. Okay, so let me start with the very simplest description. Let's think that we've got something bound to something else with a wave function phi naught describing the ground state wave function of this two-body bound system. Okay. Now let me remind you of last Tuesday's efforts. Okay. Whenever we have a model like this, where we say I've got a nucleon bound to a nucleus by some single particle wave function phi naught, we have to go through the sort of process we went through last Tuesday. Okay. What we're actually talking about is that this bound state wave function is the approximation to some many-body overlap function, which is telling me how much this A plus 1 body system looks like the A body nucleus plus a nucleon. Okay, so I don't want you to go away thinking that nuclear wave functions really look like this. Okay, this is an approximate description, and to formalize it, we go through the process we went through last week. We talk about this is a real nucleus with an anti-symmetrized wave function. We have to ask the question, what is the wave function? If I've got a process that takes one nucleon out of this system, for instance, how do I describe the relative motion of that nucleon with respect to the rest? Understanding that you start out with a many-body anti-symmetrized wave function and you end up. Okay, so let me put that proviso in. But what we saw last week was that indeed, if you choose this guy right, this overlap is a reasonable, this single particle wave function is a reasonable representation if you choose the geometry, etc. correctly. And there's also this thing called a spectroscopic factor that comes along, which tells us how much, in fact, what is the normalization of this guy that I should really use. Okay, so let's just remind you of that. Okay, but let's ask, if I had a two-body system now, like this, incident on a target. Okay, most of the time we're talking about today, I'm talking about light targets like beryllium or carbon, and so the charges are very small, and so the Coulomb effects are very, very tiny. Okay, so normally I'm not going to talk about Coulomb effects explicitly because in these systems which are very fast and with light projectiles, the Coulomb interaction will make very slight deviations to the trajectories of the particles but do very little. Okay, so let's not complicate ourselves with Coulomb. Okay, so how do we describe such a system? Elastic scattering of a bound system now of two particles from a target such as this, when this is a fast projectile of v over c, say, of greater than 0.4. Right, so how do we describe, is what I'm going to do before coffee. What can we learn from these is sort of after coffee, when I want to talk about removal, knockout reactions in which in this sort of collision that guy gets removed. What we might be able to learn from such reactions later on. But elastic scattering will be quite sufficient before coffee, I think. Okay, well, when we got composites, we need to introduce another notion, which is what's called the adiabatic or sudden approximation. Okay, so this is the advert. I think you'll probably use the word adiabatic in various contexts in physics, in thermal physics and whatever. So let's define what we mean by adiabatic here. Okay, what I'm talking about is that we've got some process happening, and I think that part of this physical system is taking place at high energy and on a fast time scale, whereas other bits of the problem have low energy associated with them and slower time scale. Okay. Now, a classic example of this, which was used a long time ago, was, for instance, if you want to do fast neutron scattering from a heavy, deformed, lumbering nucleus, okay, uranium, whatever, and you send a fast neutron on this uranium thing, which is deformed, but it has a large moment of inertia, and it takes quite a long time for this guy to want to react and to move. Okay, so one way of thinking about this, therefore, is that I'm going to calculate the scattering of this fast nucleon from this heavy deformed object as if this guy is frozen in position. I fix omega, I fix the orientation of this, and if I do that, I could calculate the scattering amplitude of this particle as a function of scattering angle from a fixed deformed object. Okay, so, and I could do that, deform it this way, and then all different orientations, I could calculate the scattering amplitude for different orientations of this body. Okay, and if I did that, somehow I've got to take the correct average of these orientations for the process that I'm interested in. Okay, and when you approach these things in this adiabatic sudden approach, what you do, if you want a physical transition amplitude where the particle comes in, encounters this object, for instance, in its ground state alpha, and you want to work out the probability of inelastic scattering of this thing to another state beta, then what you do is you have to take your amplitude calculated at fixed orientations and put the probability amplitudes for finding this object in orientation omega in the initial state on one side, and the probability amplitudes for the orientations of omega in the final state on the other side, the matrix element. Okay. Okay, this is the way the adiabatic, this sudden approximation works. Okay, so you freeze one coordinate, you work out scattering as if you've got something frozen, you get these amplitudes for any value of the frozen coordinate omega, and then you take the correct linear combination of those amplitudes according to the initial state you're interested and the final state you're interested, which will contain some functions of omega depending on the nature of these states. Okay. All right, so what it does, and we'll see this again for our composite projectile in a moment, it separates out the structure which sits on the outside of this matrix element, wave functions on the outside, and the dynamics, the calculation of the scattering, which sits in the middle. Okay, so you can calculate these two bits completely independently. I can calculate the scattering using a dynamical calculation, and then I put the structure wave functions on the outside. Okay, okay, let's add what's in this box. Of course, none of these nuclei are ever really frozen. Okay, if the moment of inertia is large, but if this is a rotational object, it'll have a rotational spectrum like this. Let's appreciate that if we do fix the orientation in the way we're doing, what we're essentially assuming is that the moment of inertia goes to infinity. Okay? It's no time to react, which says the moment of inertia is going to infinity. And if I let the moment of inertia go into infinity, then this rotational band collapses, and all those states which would normally be excited become degenerate with the ground state. Okay? So another way of thinking about sudden approximations is you assume that the energy associated with this guy is much larger than these separation of these different rotational states. So for the purpose of the calculation of the dynamics, I can just consider all these guys to have the same energy, okay? Because these energy changes are very small compared to the available energy that's being brought in by the fast particle. Okay? And we're going to do the same approximation for our composite object here. Okay? So how does that work if you've got a composite object scattering from a target? Okay? Well, we've said that we're interested in situations where the object coming in is bound and it's traveling fast. Okay? So we're going to associate the fast coordinate with the center of mass travel of this guy, and we're going to assume that relative to that fast translation of the center of mass, the internal motion of the system is relatively slow. Okay? Okay, so as we've seen, if we're 200 MeV per nucleon, this fast here means 0.6 of the speed of light. Okay? So we're assuming that the internal motion of this nucleon in its bound state is slow in relationship to this fast degree of translation of the center of mass. Okay, so what you would do in this case is that you would freeze the internal coordinate r, okay, because this object is going to scatter over a tiny time interval, something times 10 to the minus 23 seconds with this target as they go by. Okay, and so during that short interaction time of this composite object with this thing, we assume these two guys don't really have time to move at all, and we freeze them in position. And so we could calculate the scattering amplitude of these two in a fixed position from the target here. Okay, that's what I mean by this guy here. Okay, so f of theta of r is the scattering of these two objects in frozen relative coordinates from the target. And then if I want the physical amplitude, for instance, I start out in the ground state, and after the collision I end up in some breakup state in which these two are moving with some relative energy, low energy with momentum k. I would have to work out this average over the positions, the probability amplitudes for these different positions within the ground state wave function and in the final state. Okay? But it has the same structure as the one I've just been showing you. Okay? The dynamics is in the middle, calculated for a fixed position, and then you take the correct average of those fixed positions according to the wave functions, the initial and final state you're interested in. If you want elastic scattering, of course, you put the ground state this side and the ground state in that side, and you can see phi naught will tell you the probability distribution of positions between those two, and perhaps it's more obvious in the case of elastic scattering that these will simply weight these according to the probability density of the ground state. That's what elastically scatter. Okay. So going back to where we were last time, of course, this is what the spectrum of these states looks like. Okay, this may have a bound state with some binding energy, and if you excite this system up to some energy, eventually it'll dissociate and you'll have a continuum of breakup states there. Okay. Now, in the same way as in the previous transparency, we effectively chose the moment of inertia to be infinite. What we're doing here is, if we assume this to be frozen, is that we're actually assuming that the relative energies associated with this degree of freedom, little r, are all sufficiently small that I'm not going to distinguish these different final states here, and we're going to make them all degenerate with the ground state. Okay, so we got this horrible, complicated looking thing here. We never do this. Okay, we never do this. Formally, this is correct, okay, but we don't do that. What we do is use this idea, and you can see that making this approximation is to do this. Okay, somewhere in the problem you have an internal Hamiltonian that describes the relative motion of this pair, and we're going to say that relative motion Hamiltonian all its eigenstates are degenerate with the ground state. So you go back to the Schrodinger equation, and whenever this Hamiltonian appears, you replace it by this energy in the ground state. This ground state energy in the Schrodinger equation for this system. Okay, but I hope you can see this builds on the idea of a fast collision. So it goes hand in hand really with the iconal idea that we've got fast forward scattering. And this is an essential step if we want to describe few body projectiles, many body projectiles using this technique. Okay, so how do we implement that? Okay, so here we are. Here's the way you would implement it if you wanted to do either a Schrodinger equation calculation or an iconal model calculation of this sort of system. Okay, so here's our Hamiltonian. I think we've all seen several of these last few days now. Okay, so two bodies for simplicity interacting with a third. There's a ground state wave function, particle 1, particle 2. And so the total Hamiltonian is a kinetic energy for the center of mass, an interaction of particle 1 with the target, an interaction of particle 2 with the target, and the internal Hamiltonian that describes this system here. Okay, here's our definition of our coordinates in terms of the masses involved, and the Schrodinger equation will look like this. Okay, and the boundary condition is that on the full wave function is there's an instant plane wave in the r coordinate times the ground state wave function of this pair, and after that there's all sorts of other stuff involving dissociation, breakup, excitation, and elastic scattering of this object. Okay. Right, so as you said, if I want to do this the adiabatic way, then it says, well, I need to neglect the internal excitations associated with this internal Hamiltonian, and we go back to the Schrodinger equation. Whenever H int appears, we replace it by the ground state energy. Okay? So that's the way you implement the adiabatic approximation, and so now your Schrodinger equation doesn't have this Hamiltonian in. It's been replaced by that, and the equation looks like this. Okay, where ECM is the instant central mass energy of the projectile in its ground state. Okay, now you'll see, hopefully, that in this equation R is just a parameter. Okay, no dynamics to do with R in this equation. R will appear in this potential because the radius of this potential of 2 with the target involves little r, for instance, but there's no del squared in little r. There's no differentials in little r. R is just a number, and I can calculate this equation here for any value of little r. Okay, that's what I was saying in the previous. I would like to calculate the amplitude, the solution, for any fixed value of r, and this equation has that property. There's no dynamics in here. R is a parameter, so I can solve this equation for many, many values of little r, and then we use them as we need to afterwards. Okay, I'm going to leave this one is just for those who are more theoretically inclined. If you want to think about what is the condition for this adiabatic approximation to be working on a timescale perspective, then you can write this down with some time-dependent operators, and I'll leave that to those who are more interested in it. Okay, but at the end of the day, the important thing is this thing down here. Okay, if this is going to be a good approximation, it must be such that the typical energies associated with the internal Hamiltonian of the system plus the binding energy here times the collision time, this quantity should be a lot less than 1. Okay, if that's true, this is fast enough to freeze that coordinate. Okay, so we've got ideas of the collision time based on our earlier diagrams, and so we could see over what sort of range of excitation energies this might be true for this approximation to be true. Okay, but we're going to use it for the time being, and we can test it later on. Okay, so we need the time scale, but I'm suggesting if you want to look at that equation and judge whether the time scale is good enough as a function of energy, these are the time scales, these are the collision times we had, and you can go back and look at that former expression and make an estimate for yourself. Okay, so let's go now. We've got an adiabatic Schrodinger equation. This is our guy, okay? This is our three-body Hamiltonian now, and R is a parameter in here, and so having made the adiabatic approximation for each fixed value of R, I can solve this guy. Okay? And because the name of this session is iconal, we're going to solve this guy in the iconal way. Generalize what we did before. Okay? So that's fine. Okay, so here's our instant plane wave. It's now a plane wave times the ground state. So just as we did before, I'm going to look for a solution of this, which has the form of the instant wave times the ground state times a modulating function. Okay? It's what we did before, right? Instant part times a modulating function. So I would like to solve this equation to find out what omega is. And seeing as this is what the instant boundary condition looks like, apart from the omega, we can see that when I go a long way down in the minus z direction before the collision, omega must go to 1, because that's what the instant plane wave looks like. Okay, so down here at r large and negative z, omega must be 1, and then as z approaches this way with an interaction region and goes through this way to positive z, interesting things will happen. Okay, so as before, we plugged this. R is just a parameter, remember, so we plug this guy into the Schrodinger equation. We differentiate out the products, as we must, and we get this term. And the only difference from last time is really that I've still got my linear term, I've still got my curvature term. Now I get two terms here, one from interaction 1 and one from interaction 2. Okay, R's just a parameter. Let's go on stressing. R's just going along for the ride in this expression. Okay, and so fine. Same thing as before. I throw away the curvature term. I've only a component of the gradient in the z direction. And now this has a sum of two terms. And so when I write down the sum of this first order differential equation as an exponential function, I have a sum of two potentials upstairs. So I've got the exponential of a sum. And the exponential of sum is the product of exponentials. Okay? And so what you'll see that, and this will generalize to 3 particles, to 4 particles, to 5 particles. What we can see is that this modulating function, these different particles that are appearing with their own interactions enter in the exponential as a sum. Okay? And so we've got, just as we did before, remember R is frozen. And so I've got these two in a fixed position, and they're traveling through past the interaction region with some velocity v, and they're on their own straight line paths at their own individual impact parameters. B is the impact parameter, the center of mass of the object. B2 is the impact parameter 2. Okay, so we need to do these integrals along the z direction for particle 1 at impact parameter b1, particle 2 at impact parameter b2, etc. But the most important thing here is not this expression, but our modulating function is now the product of this exponential, which is the S matrix element for particle 1 scattering independently of particle 2, and this one, which is the S matrix element in the Glauber sense for particle 2. Okay? That's what I was advertising before. Okay? So if I go from single particle to 2 particles, the 2 particle dynamics comes in a very simple way, just the product. If I go to 3 particles, there'll be 3 of them, 4 of them. 5. When I did helium-8 a long time ago as an alpha particle and 4 neutrons, I'll show you at the end the product of 5 S matrix elements, 1 for the alpha particle, 1 for each nucleon. Okay? Okay, so that's the key thing. That's the key message I really want you to take away. And let's see if we can rapidly finish this. Okay, so that's the summary for a composite. Okay, I've done it for 2. What you can do if you do this more generally is that you get each phase is given by each interaction. The total interaction energy is the sum of these 2 body interactions, and so I end up with an exponential, I end up with a sum in the exponential every time, and so I get the product of S matrices as a general result from coming from this. Okay, we've done it clearly with 2, more generally. Okay, so after the collision then, remember we started out down here at large negative z, where the modulating function was 1, and then we integrate through the interaction region and we come out the other side as z goes to plus infinity. Okay? And when we go to plus infinity, we get the S matrix. And so you can see that our iconal wave function, once I come through the interaction over here, is omega's this. And so the wave function looks like S of the core, S of the valence particle, ground state wave function, and the instant plane wave. That's our modulating functions gone in there. Okay? So if I want to know the elastic scattering of this composite particle, what I have to do is put these guys SC and SV, which is the omega between the ground state and the ground state, and this will calculate a scattering amplitude that depends on the impact parameter of the center of mass of the object, and this is the elastic S matrix of the composite from which you can calculate the elastic scattering. Okay, so using the language that we had before, these are S's here. So they're telling us the amplitude that C and V survive the interaction with their fixed values of BC and BV, and then we're taking the average over the values of the relative coordinate, which are actually present in the ground state wave function, because we've got the projectile coming in phi naught, and I want to find the probability that it goes out of the collision with phi naught as well. Okay, so this is this separation of the dynamics that I talked about. Okay, so the way iconal theory works for a many-body projectile such as this, as I say, there's stuff in the middle describing the scattering, and there's wave functions at the outside that discuss the structure. Okay, so if I want the S matrix element telling me the transition from an initial state alpha to initial state beta, we can calculate the scattering, compare that with the experiment. If I've got data for particle C and data for particle V, I can work out these S's and check that they compute the right cross-sections for the elastic scattering. And having determined that these S's are good S's, then I need a nuclear structure wave function, the best I can take, so that I can put it on the outside to tell me what I think the correct structure is in working out this matrix element. Okay, so that's for two bodies, and as we said, more generally, if I take any choice of clusters or nucleons, 1, 2, 3, up to n, you generalize in the same way. Okay, what comes in the middle is the product of the S matrix for the bits, and then you use the best wave function you can find on the outside for an n-body system, if that's the way it's been described. Okay, these are functions of B, and so if I want the cross sections, then the result will be to integrate these S matrix elements essentially over all impact parameters to give me a cross section for the transition from state alpha to state beta and so on. Okay, so I hope you get the structure of it, okay, because the structure is important for what I want to do this afternoon in terms of a specific reaction. Okay, so this is that example that I referred to. As I say, if you do things the normal way, treating with a 5-body projectile scattering from a target is essentially an impossible task as we're set up at the moment to do things. Okay, from a fully microscopic point of view, in this coupled channel sense that we discussed yesterday, it's really tough. Okay, let me indicate here from what we've done this morning. Okay, so this is an example. The energy was a bit low, but the data was also had some reasonable error bars. Okay, so this was a first attempt to try and understand these data in terms of the microscopic structure of helium-8. Okay, so you will see now, you should recognize this now. If you want to work out the S matrix element for helium-8 scattering from a target nucleus, what I need is if this is an alpha particle and 4 neutrons, you worry about the coordinates, how you describe them, plenty of choices how you describe your coordinates. But you need an alpha particle S matrix. You've got 4 neutrons, so you need the product of 4 neutron S matrices, describing neutron carbon-12 scattering in this case. And then you need to sandwich those between some wave function that tells you how the ground state of helium-8 depends on these different coordinates of the particles. Okay? And in this work, this was quite a simple wave function, something called a cluster orbital shell model interaction, very similar to a cluster interaction, and basically it contained an alpha particle and 4 nucleons moving about the alpha particle in a correlated way in p-wave orbitals, as you might expect to be the structure in helium-8. Okay, but you can do it. You can do it. It was done. And this is a comparison over here. The data that was taken weren't actually elastic scattering data. Unfortunately, they were quasi-elastic scattering data. And but there is a curve on here, which is a solid curve, which shows the prediction of this calculation, where one calculated the elastic scattering, and which is the dashed curve using this model, and then added on an estimate of the inelastic scattering to the 2 plus and the 3 minus states of carbon. And you can see it goes somewhere near the data, indicating that the physics is put in somewhat reasonably. Okay. If you're thinking about what these open dots are, those are the corresponding data for lithium-9 scattering, and the solid points are for helium-8. Okay. Okay, so that's the advert to show that this allows us to do things for more complicated systems that are difficult to do more exactly. Okay, but bear in mind, right from the start, these are approximate procedures. They require certain approximations to be made, and we have to assess in each case whether we're at high enough energy that the iconal solution is good, and that the adiabatic step, the additional frozen step, that the collision times are sufficiently short that we don't have massive arrangements of these things in the time of the collision. I think that's probably my last. Okay, so you can do things. Okay, I hope you've seen from what we got, to carry through this procedure for scattering such as I've talked about this morning, I'm going to need bound states, because those are the things that sit on the outside of the matrix element and describe the structure. But we know we've got routines to calculate bound states. You've got your old mate bound sitting there. You run that last week. Okay. Then we need potentials, right? Because I need U's so that I can construct the S's. Okay. We need optical potentials. So the other thing we need is to be able to compute some optical potentials, but we know about those. You know about global optical potentials. You know now where to find optical potentials. Okay. So given bound states, we can talk about composites. If we're given an interaction, we need the means to calculate the iconal S matrix by doing those integrals along the Z direction to calculate the S matrix as a function of impact parameter. So that's what this guy does for you. Okay. If you want to look at elastic scattering, you then need to take that iconal S matrix, add on the point Coulomb, and do the other bits. Okay. So that's what this one will do for you. Okay. And this one we'll be using this afternoon more. It does other things. But what it'll also do for you is work out this. It'll work out this guy for you. Okay. So if you choose potentials, if you compute an S matrix for beryllium-10, say, and you compute an S matrix for a neutron, you calculate your bound state bound, which describes the bound state of these systems. It gives us a probability distribution for finding those two at different positions. Then this last code will do that calculation for you and will spit out an S matrix element for this composite object, and then you can calculate using this guy what the elastic scattering therefore is of a composite object. Given any S matrix, you can calculate the composites, the elastic scattering using this code here. Okay, so I think you do many things to try and get an idea of how accurate these things are. Okay, so there's my summary of what we've tried to talk about this morning. Okay, I've shown you how we can take the Schrödinger equation for 2, 3 more bodies at high energies, whatever that means. Be careful. Okay? You need to interpret that as physicists. By using the iconal solution, forward-dominated solution, and in addition we need to make this adiabatic approximation when we're talking about more than 2 bodies and composites. Okay? I've tried to once again highlight the importance of these S matrices in terms of a survival probability versus an absorption probability in the reaction, because we're going to live with that this afternoon. Okay? And I've discussed some examples such as neutron scattering and beryllium-10 scattering, where you can start to assess the accuracy of these things. Okay, and if one understands all this stuff, then I think one understands a reasonable amount about what the philosophy of attacking the problem in this way is. Okay, so that's the only thing that's left is some sustenance, I think. Okay, but happy to answer questions individually if anybody has questions that immediately come to mind.